Well, welcome back. This is Unit 6.1. We're starting a new unit today, and this unit is on chemical reactions. This information can be found in Chapter 11 of your textbook. Well, before we start talking about chemical reactions, we have to get clear the chemistry or the chemical shorthand that's going to be used. We need a method of writing chemical equations that's quick, like texting is quick. Because you don't spell out every word when you text, you use a lot of abbreviations because that's a quick kind of communication. Chemistry does the same thing, and this allows us to see the interactions of the compounds and the molecules that are happening without having to work around all the wording, the big heavy words that are there. So Joseph Priestley in 1774, which was right about the American Revolution, because that's 1776, discovered that by heating a solid compound that he could produce mercury, metal, and oxygen. Now the explanation or the word equation for this is mercury 2 oxide, which is a solid powder, can be heated to a point where it decomposes into a silver liquid, and in the process, a colorless gas called oxygen is liberated. Okay, so that you can see there is big and bulky and very wordy. So if we write the chemical equation, we're going to have here HgO, which is mercury 2 oxide. It's a solid, so we put S in parentheses. And when it's heated, it breaks down into liquid mercury and oxygen gas. So the equation here includes these abbreviations that you see. So S in parentheses is solid. So that just means if you see something in parentheses after a compound or element, something like this, that's just telling you what state it is in. Okay, so L, and it can either be a Times New Roman L, which looks like a 1, but if it's in parentheses like this, then that's really an L. And so you can see here, a lot of times they'll write them in script like this so that there's not any confusion. And that means that it's in the liquid form. Then sometimes you'll see G, and this is gas form. And a little later on in chemistry, we're going to start seeing AQ. AQ just means it's aqueous. That means it's dissolved in water. Okay, then we have this symbol, which is the arrow like this, and that means yields or produces. And then we have, sometimes you're going to see, again, a little later on in chemistry, a double arrow, one pointing to the right, one pointing to the left. Sometimes it looks a little different than that. Sometimes it looks like this, with the two lines on top of each other. And then we just see half of this arrow so that those 2 points don't, overlap and interact with each other. It looks like this. And that just means that it's reversible. The reaction will go both ways. It will go to the right and go to the left. And it's what's called an equilibrium reaction. Okay, and so we look at a chemical reaction, and this arrow here that we see is really what separates the reaction into the two halves. We have two halves of reaction. Everything that's on the left side of the reaction are called reactants. And then everything on the right-hand side of the reaction are called products. So these are just some vocabulary words that you're going to see used and thrown around. So you need to know what it's referring to and what it's talking about when we are, working with these chemical reactions. Okay, so that's your chemical shorthand. And that's how we write chemical equations. Well, let's talk about balancing reactions. And I know that you've talked about balancing reactions a little bit in junior high, but we're really going to get into it in chemistry. And this is just going to be really the backbone from this point forward of the rest of the chemistry that we have for this year. Well, historical evidence connects Joseph Priestley's experiment with the decomposition of mercury 2 oxide with another famous chemist. He's a French chemist. His name is Anton Lavoisier. So the OI in French makes a W sound, so it's Lavoisier. Okay. And Lavoisier used to like to measure things. He liked the quantitative part of chemistry. And so he's credited with what's called the law of conservation of mass, which back in his time in the French Revolution was a very radical idea, very radical. It was so radical that he eventually lost his head to the guillotine during the French Revolution. Okay, and you may know the French Revolution. You've talked about the French Revolution maybe in world history. It's Les Miserables, the musical. It's about the French Revolution if you're into musical theater. Or you may remember things like Marie Antoinette, Let Them Eat Cake, things like that. That's all the storming of the Bastille, Bastille Day. That's all resulting from the French Revolution. Well, back to the law of conservation of mass from Lavoisier. The law of conservation of mass says that matter cannot be created or destroyed, only changed and rearranged. So every atom in a chemical reaction has to be accounted for from the reactant side to the product side in equal numbers of atoms. Okay, so as this equation as written right here, it does not obey the law of conservation of matter. Because for one example, here we have 2 oxygen atoms. Okay, and remember, it's the arrow that divides the 2 sides that we're looking at. So here on the product side, we have 2 oxygen atoms, where over here we only see 1. So this is not a balanced reaction. Okay, so every reaction that we work with in chemistry has to be balanced and has to obey the law of conservation of mass. So we do this thing called balancing equations, where we make sure that those are balanced. And the way we do that from right to left is by adding coefficients. And a coefficient is a number. Oh my gosh, I misspelled that terribly because I'm trying to talk at the same time. Is that spelled right? Coefficient. My spelling is horrible. All right, so a coefficient is a number that you put in front of a chemical compound, and it multiplies how many of that compound that we need. You cannot balance an equation by adding subscripts like this, because a subscript is going to change the chemical formula, and we do not want to change the chemical formula. We just want to change how many of that formula that we have. And so we do that by adding coefficients in front of these compounds. Okay. And so let's go through this one really quick and look at how this one will be balanced. So what I like to do when I first start teaching about balancing is I tell you to take all of the atoms that are the reactants and list them underneath this arrow, because remember, the arrow is what divides the right and the left. So we have mercury as one of our reactants over here, one of the atoms that are reacting. We also have oxygen that's over here as a reactant. So we're going to have the same mercury and oxygen on this side, but we have to make sure they're in equal amounts of atoms. So if we list them under the arrow here, it makes it easy for us to compare right and left. So let's just look at the mercury. So on the reactant side of this equation, we have 1 atom of mercury. So if we go over here to this side, we have 1 atom of mercury. So those are balanced. That's okay. So now let's go to the oxygen. If we look on this side, the reactant side, we see here that we have 1 atom of oxygen. And on this side, we have 2. This tells us we have 2 atoms of oxygen. Remember, counting atoms, those subscripts tell us how many of those that we have. Well, this can't work because we have 2 on this side, we have 1 on this side. So it looks like we created an atom of oxygen. Remember, we cannot create or destroy matter. Okay, we can only change it. So what we have to do to balance this is we have to say we need 2 of these molecules. Because this 2 is a multiplier, it multiplies the amount of oxygen. So it's like writing this. Okay, and then writing it again yields this. Okay, so see here we have 2 of these oxygens, which balance these 2 oxygens. So now I can cross this out. But since we added another mercury 2 oxide here, it's changed the number of mercuries we have. So this side we have 2, but this side we only have 1. So sometimes when we change this, we have to backtrack and rebalance something up in that we've already balanced. So if we have 2 mercuries here, we have to have 2 on this side. So we need to add another one here. So let's add a 2 coefficient here. So that makes that 2 on this side and 2 on this side. So as we have this written here, this is balanced. 2 mercuries, 2 mercuries, 2 oxygens, 2 oxygens. So this is, we don't write it out this way. So we use these coefficients here instead of writing multiple compounds. And so we have 2, and this means we have 2 moles. Okay, so remember we measure, in chemistry, we measure compounds in moles. So when you're reading this, we have 2 moles of mercury 2 oxide yields 2 moles of mercury plus diatomic oxygen. Remember, these are diatomic molecules. Horses need oats for clear brown eyes. So diatomic molecule, so diatomic oxygen. Okay. All right. So let's balance a couple of equations. All right, so here we have H2O, water plus silicon tetrachloride yields silicon dioxide and hydrochloric acid. So now we're going to have to start taking equations. We learned about naming already, right, in formula writing. So we know how to name these. So we're going to get to a point where we have equations written out, and we're going to have to rewrite them here like this using symbols. All right, so let's write all of these out. Now, what I like to do is I like to save carbon, hydrogen, and oxygen to the last, because a lot of times they appear in multiple places, so it makes it easier to balance. So if I have hydrogen or oxygen, I'll wait to write that until I've written the other ones. So here I have silicon and chlorine. Okay, so that takes care of this, nothing else. So I don't have carbon, so I'm going to write hydrogen and then oxygen here. Okay, and so we're balancing this left to right. Remember, the arrow is the separation between the reactants and the products. So silicon, we have 1 here and 1 here. So that seems to appear to be balanced. Chlorine, we have 4 here. We only have 1 here on this side. So we're going to have to add a coefficient of 4 here in front to make 4 chlorines. So now that's balanced. Now we can come to our hydrogen. Well, here we have 2 hydrogen on this side, but we have 4 hydrogen on this side. So we're going to have to make 4 on this side. So if we add a 2 here, 2 times 2 is 4. So that makes 4 hydrogen on both sides. Now finally, on the oxygen, we see here on this side, we've got, see, this is a multiplier for everything. So we have 2 oxygen on this side. And if we look over here, we have 2 oxygen on this side. So that's why I say save carbon, hydrogen, and oxygen to the last, because sometimes it balances itself out and you don't have to do any more adding of numbers. So 2 oxygen, 2 oxygen, everything appears to be balanced. But what you need to do is make sure you go back and recheck everything once you think you have this equation balanced out like it should be. So I'm going to just, oops, I erased the top part of my 4 there. Didn't want to do that, so let me add that back in. So we're going to go and we're going to make sure this is balanced. 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen, 1 silicon, 1 silicon, 4 chlorine, 4 chlorine. So there's your balanced chemical equation. Now we can use this balanced equation in other calculations that we may want to do with this equation. So it's very important. You have to start everything you do in chemistry with a balanced equation. Okay, so that's why it's so important that we learn how to balance equations, because we can't move forward in chemistry without a balanced equation. All right, one more. So here's our arrow, here's our dividing line. So lithium. Okay, now here we have polyatomic ions. We have a polyatomic ion OH hydroxide. So instead of busting this up into oxygen and hydrogen, let's look on this side and see if we have that same polyatomic ion, and we do. Well, if that's the case, let's keep that polyatomic ion together and balance it as a polyatomic ion. It makes it tons easier. Okay, so here we have iron, and here we have another polyatomic ion, IO4. Iodate, so let's look over here. We see IO4 over here, iodate, so we can go ahead and balance that as a polyatomic ion. All right, so simple. So here we go, counting numbers. Lithium here, we have 1 on each side, so that's good. We have 1 OH here, and we have 3 OHs on this side. So we're gonna need to have 3 OHs on this side. All right, now we see here that that's messed up our lithium. So let's go ahead and correct this. Actually, I don't want to cross the whole thing out. Let's go ahead and correct this before we move on. So now we have 3 lithium on this side. So let's make 3 lithium on this side. It just makes balancing a whole lot easier if once you see something's changed, you backtrack and fix it before you go on to the next one. All right, so we have 3 hydroxides, 3 lithium, 3 lithium. So to this point, it's fine, it's balanced. So now we can move on. So we have 1 iron here, 1 iron here. So that appears to be balanced. Now iodate, we have 3. See this 3 outside the parentheses says we have 3 of those. So we have 3 iodates on this side. And if we go to this side, IO4, this 3 also multiplies that. So we have 3 iodate on this side. All right, so this appears to be balanced, but always go back and double check your balancing before you try to start using this, because it gets really frustrated in chemistry when you think you have a balanced equation and then you start doing other calculations and then you go back and look and you see that it wasn't balanced correctly in the first place, so you've wasted a lot of time. So it's always good to make sure you double check. 3 lithium, 3 lithium, 3 hydroxides, 3 hydroxides, 1 iron, 1 iron, 3 iodate, 3 iodate. So there you go. That is a balanced equation. We're going to have a lot of practice balancing equations. So if you didn't get it on these 2, that's okay. Lots more practice to come. All right, so let's pause the video and write down these statements, these tips and tricks to help you balance equations. All right, so first, make sure all of your formulas are correct. Again, there's nothing more frustrating to get to the end of balancing an equation and it won't balance. You're like, you keep going back and forth and this just isn't balancing, probably because you have a wrong formula. It's never going to balance if one of your formulas are not correct. So make sure all of your formulas are correct. Always save carbon, hydrogen, and oxygen to balance last in that order, because again, they often appear more than once in a chemical reaction. So if you save them to the last, it just makes balancing easier, because a lot of times they balance themselves out as you're balancing the other elements in the equation. Start with polyatomic ions that appear on both sides of the equation. So if you see a polyatomic ion as a reactant, make sure to look on the product side to see if you have that same polyatomic ion before you start busting them up into different elements. A lot of times it's easier to rewrite H2O as HOH. You can see how things balance because, like, say, for example, OH, the polyatomic ion, if you have OH on the right-hand side, maybe, but you have H2O on the reactant side, and it's written as H2O like this, you may not see that that polyatomic ion occurs on both sides. So from here on out, a lot of times it's easier to write H2O water as HOH. Okay, so that's just a little trick. When you add a coefficient to one side, finish balancing the rest of the atoms of that species before moving on to another. Okay, and also once you balance something from that changes something before it, go back up and backtrack, fix it before you move on. Okay, if our numbers start to get crazy high, like over 30 or something when you're balancing, then and you have to keep going back and forth, like you'll balance something on the left and then try to balance it on the right, and you fix it on the right, but then it unbalances it on the left, and you have to keep going back and forth. Chances are you have a wrong formula written down somewhere. So something went wrong. So instead of banging your head against the wall, just erase what you've done, start over, and recheck your formulas. Because 9 times out of 10, it's going to be a formula that's been written wrong when you're going from words to formulas. Okay, always perform a final check. I think I mentioned that already. Once you think you have an equation balanced, go back and recheck it before you move on. And we're going to see, I haven't showed you this yet, but we're going to see a half a molecule trick for diatomic elements that's really helpful in balancing. And this happens most often in what's called a combustion reaction. When we get to combustion reactions, I'm going to show you that half molecule trick. So go ahead and write that down now, but remember that for future. All right, so let's talk about the 5 different major categories of reactions. There's 5 different major categories of reactions. Okay, and the first one is a synthesis or combination reaction. And here's 2 examples. In a synthesis reaction, synthesis is a scientific word that means to make. Okay, to make. Okay, they're also called combination reactions because what you're really doing is you're taking 2 elements and combining them to synthesize a compound. So here we're taking phosphorus and oxygen, we're combining those to make P2O5. Okay, now it's also possible to take 2 compounds like this one, combine those together into one more complex compound. So some things to look for to see if a reaction is synthesis is you only have one product. Okay, so you start with multiple reactants. Here we have 2 reactants, but you always end up with one product. So see here we have 2 reactants, and we're going to end up with one product. That's a telltale sign that this is a synthesis or a combination reaction. Okay, the second one is decomposition. It's kind of the opposite of a synthesis reaction. So you're taking a compound, and usually you're going to heat it, and it's going to break it down into a simpler form. You're either going to get 2 simpler compounds, or you're going to get 2 elements. So the thing to look for on decomposition, remember decomposition means to break down, decompose, uncompose, break it down. The thing to look for is you have one reactant here, and then it's going to be broken down into multiple products. Okay, one reactant, then you have your arrow in multiple products. That's the telltale sign of a decomposition reaction. So our next reaction is called combustion reactions. And when I ask students, what does combustion mean? Like if I ask you right now, what do you think combustion means? I bet in your head you're thinking explode. Okay, because that's usually what students say. Combustion means to explode. Well, it really doesn't. Combustion means to burn. Okay, to burn. So to combust something means to burn it. Okay, so in a combustion reaction, we usually start with what's called a hydrocarbon. And a hydrocarbon is just carbon combined with hydrogen. This molecule here is carbon and hydrogen, so it's a hydrocarbon. And we're going to combine that with oxygen, okay? And we're going to add a spark or some kind of heat source, and it's going to react, and it will always produce, there's always produce carbon dioxide and water. And this happens in the engine of your car. So you take your gasoline, which is a hydrocarbon, okay, ethane usually, and it is injected into the piston chamber by an injection mechanism. So it really causes it to evaporate. So you have the gas, and then a spark is provided through the spark plug that ignites the gas. Okay, it burns and it produces carbon dioxide and water. And so what comes out of your exhaust pipe is carbon dioxide exhaust, also carbon monoxide, okay, and water. So it does produce water. Now, if you look, especially this time of year when it's cold, maybe notice as you're driving to school or as you're being brought to school by your parents or brother or sister or somebody, look at the cars that are ahead of you at the stoplight. You can see this smoke coming out of their tailpipes. That's really not smoke. Well, maybe sometimes it is if they have, engine problems, they may be burning oil, but most of the time it's really not smoke. It's water vapor. Because it's cold outside, you can see that water vapor coming out of the tailpipe. And if you look really closely, especially if they just jumped in their car and took off, they haven't been in their car very long and the engine's still kind of cold, maybe warm, not really hot. Sometimes you can see from the tailpipe little droplets of water that are dropping out. That's because this water vapor that's being released in the exhaust is condensing on the cold edge right here, the edge of their exhaust tailpipe. It's condensing there because of the cold. It's still cold and it's dripping water. Okay. And so sometimes this causes rust on the tailpipe and the tailpipe rusts out. You have to have your tailpipe or your muffler changed out because it's rusted out and now it's causing a loud noise. Okay, but watch for that. That's what happens. So back to the combustion reaction, combustion, you always take a hydrocarbon. Okay, and this is the part that changes. In a combustion reaction, this part never changes. It's always a hydrocarbon combined with oxygen, and it produces always, the two products are carbon dioxide and water. Every single time, never changes. Okay, this is called a combustion reaction. Now, remember earlier I told you about the half molecule trick? I'm going to show you that now. Okay, so here is where we're going to use that trick. Now, this is already balanced because it tells us 2, 25, 16, and 18. Now, in combustion reactions, you're going to get high numbers like that. That's typical. So let's go ahead and I'm going to rewrite this without it being balanced. So I'm going to write it without those numbers there. And we're going to see how we use that half molecule trick. Okay. All right. So here's what's called the skeleton equation. Skeleton equations are unbalanced equations. So we're going to do carbon, hydrogen, oxygen in that order. Okay, just like I said before. All right, so carbon, here we have 8 carbons on this side. Over on this side, we only see 1. So we're going to add an 8 here to make 8 carbons. Okay, so it's balanced from right to left. Now hydrogens, here we see 18, but here we see 2. So what number can I put here that's going to multiply by 2 to give me 18? Well, that's going to be 9. 9 times 2 is 18. So did we change the carbon? No, because we added a 9 here. There's no carbon here. So that didn't change the carbon, so we don't need to backtrack. We still have 8 carbons on each side. So now here we get to the oxygen. Well, we have oxygen in one spot here, but we have oxygen in 2 spots here. So what I like to do on these equations is I like to count this side first and then match this side. So here we have 8 times 2 is 16 oxygens here, and 9 times, there's a 1 there. We don't write ones though. So 9 times 1 is 9 oxygens there. So on this side here, we've got 25 oxygen. So now we need to match 25 on this side. Well, here we have a 2. So what can we put here to multiply by 2 to get us to 25? Well, that's going to be 12.5, 12 and a half. 12 and a half times 2 is 25. Well, we can't have half of a molecule. We can't have 12 and a half molecules. There's no such thing as a half a molecule. You can't just slice a molecule in half. This has to be a whole number. Okay, so we're going to fix that by multiplying everything in this reaction by 2. So when we do that, we get 2C8H18 plus 2 times 12 and a half is 25 oxygens. And that's going to yield 2 times 8 is 16 carbon dioxides plus 2 times 9 is 18 H2Os. So once we've done that, we have whole number coefficients, okay? And it balances out. How do we know that? Because it equals this equation that we're given here. So this is the half molecule trick that I was talking about. Go ahead and put in a half here because we know that we're going to multiply everything by 2 to get that to a whole number. Okay. Sometimes it works out where you don't have to do the half molecule trick, but sometimes you have to use this little trick to get these combustion reactions to work out. Okay, the next type of reaction is a single replacement reaction, and sometimes these are called kick-out reactions because what happens is you have one element that kicks out another element and replaces it in a compound. Now, we have to make sure that we check what's called the activity series to see if this is going to be even possible. So if you look in your reference materials, you're going to see an activity series like this, and it tells you that lithium is going to be stronger than rubidium, which is stronger than potassium. So these are in the strongest down to the weakest metals down here at the bottom. Stronger metals replace weaker metals. Weaker metals cannot replace a stronger metal. Okay. So if you have a weaker metal trying to replace a stronger metal, then it's not going to react. There's not going to be a reaction there. So you have to keep a lookout for those. Okay. And another thing to keep a lookout for is metals replace metals. So positive ions can only replace positive ions. Nonmetals can only replace nonmetals. Okay. And here's your list. It's the periodic table. The strength of the nonmetals, they're usually halides. So fluorine is stronger than chlorine, which is stronger than bromine, etc. So you go by this to see if these reactions will even happen. And then metals can also replace hydrogen to make hydrogen gas. So let's look at this. So here we have a metal. Here's another metal. So this metal is going to try to kick out this metal. Is that even possible? So let's check potassium. Where's potassium? Right here's potassium. So K is potassium. And is it stronger than copper? Is it able to kick out copper? Well, here's copper here. So yes, it's way much stronger. So potassium is going to kick out copper. Copper is going to be here. And potassium is going to replace copper in this. So we have KNO3 right here. So now the reason we see here that we have 2 NO3s here with copper and only 1 here with potassium, it has to do with the charges. Okay, so this is copper 1. Okay, this has a charge of 1, so I'm sorry, 2. because nitrate is -1. So we know that copper 2, this is copper 2 because we have 2 nitrates here. So we had to have 2 -1s to make this balance out to 0. Remember swap and drop? Okay. Now, since nitrate is always a -1 and potassium is a +1, you only need 1 here to do that. Okay. So we can't change formulas. We just don't automatically come over here and write NO3 just because it's on this side. Remember, we have to balance out those charges. So that's why it's written the way it's written. And we just use coefficients now to balance out these atoms. So here we have 2 NO3s. So we're going to have to balance this by doing 2 KNO3 here. And there you go. The 2 balances this 2. Okay, so I want to make sure I point that out. Just because you have 2 here does not mean it's going to be parentheses 2 here. That doesn't exist. Okay, so you have to look at your charges. All right, but that's a single replacement. This single element is replacing this single element. Kick out, it kicks it out and takes its place. Okay, so that's metal replacing metal, non-metal replacing non-metal. So here we have bromine, which is a non-metal. It's going to replace this non-metal, iodine. It's going to kick it out. Okay, so here we have iodine kicked out and Br took its place. All right, and then we have metals replacing hydrogen. So this metal replaces or kicks out this hydrogen, creating hydrogen gas. Now remember, hydrogen is one of those diatomic elements. So here we see it kicks it out, but there's just one hydrogen here, but this doesn't exist. When it's by itself like this, it has to be diatomic. It has to exist as H2. So that's one of those 7 diatomic elements. So we had to have a 2 here, and we fixed that by balancing the equation. Okay, balancing the equation. All right, so those are single replacement reactions. And the last is a double replacement reaction. So double replacement means 2 things are going to be kicking out each other, or they're just going to be swapping. So what I like to remember on this side, this type of equation is inside, outside. Inside, outside. What does that mean? Well, that means that the inside elements are going to combine. So inside, so Ag is going to combine with Cl. There you see it right there. And the outside ones are going to combine. So we have Na combining with NO3, the polyatomic ion NO3, Na, NO3 there. So inside, outside, when you have 2 compounds like this, it's called a double replacement because 2 things are happening, double, 2 things are happening. Inside is combining and then outside is combining. That's how you get your products on that. Okay. And I know that some of these aren't balanced. Like if we look back at these, some of these weren't balanced. That's okay because I'm just showing you the type of reactions. Okay. That concludes 6.1. For this is just the basic types of reactions. Later on in this unit, we're going to look at specific types of single replacement reactions and specific subcategories of double replacement reactions. But for now, just learn the 5 different major types of reactions and you'll be okay. All right, so give me a thumbs up. Make sure you slap that like button right across the face, and we'll see you in class.